Hi everyone. Today we are going to be going through section 10.2 from the textbook, which covers sequences. Right, so moving away from section 10.1, which is just kind of an overview of what we're going to talk about during this entire chapter 10. Now we're actually going to get into the specifics of how you prove things about sequences. So in this section, we're going to specifically be interested in showing when sequence converges. So when do sequences converge? And this is going to be particularly helpful in the rest of the chapter because a lot of the rest of the chapter will be dealing with series, right? And convergence of these infinite series, as we talked about last section, is the same as the convergence of the sequence of the partial sums. So we'll be using all of this material in the rest of the chapter in dealing with the convergence of infinite series, which we're a bit more interested in. Okay, so let's first start by going through a couple of limit rules for these sequences, and then we can talk about some techniques we can use for actually showing that they do converge. So limit rules. And these should look very similar to rules you already know, especially rules for limits of functions rather than rules for limits of sequences. So let's say that I have two sequences. Limit as n goes to infinity of my a sub n. And we'll say it equals a. And a limit n goes to infinity of my b sub n equals just some number b, where a and b are not positive or negative infinity. Then we have the following limit rules. So if we take all of the terms in our sequence and add them together, so the limit as n goes to infinity of an plus bn, well, this is just going to be a plus b. So we're just combining our two sequences by adding them together. And the same thing is going to hold if we subtract them as well. So plus or minus there. Furthermore, if we introduce a constant, so we just take all of the terms in our sequence and multiply them by some constant c, this is the same as taking c times a. Okay. Similarly, we can do the same thing with multiplication. So infinity of an times bn now. And this is a times b. And then we can do the exact same thing with division. An divided by bn equals a over b if we don't have b as 0, right? Because otherwise you're dividing by 0, which is something we don't want to do generally in mathematics, right? This will lead to positive or negative infinities, which we don't want to do. So you need to make sure in this case that your b is not equal to 0. Okay, so the first technique that we are going to talk about for dealing with these limit rules is going to be just converting them into the world of functions. So let's say I have a sub n is f of n for some function f, for some, and I think we need it to be continuous. Continuous function f. Then we need this limit as now x goes to infinity of f of x equals L. So if the limit of this function exists, then the limit of the sequences is the same as this function. Then goes to infinity of a sub n equals L. Right, so the best picture to think for this is, say we have some n values, and some a sub n values. And we kind of get this idea that they're going to be approaching some asymptote right there. All this is saying is that if we can find this nice function to connect the dots here, well, and obviously better connecting the dots than I can draw, we can deal instead with the function instead of with the sequence. And the reason this is nice is that we have a lot of different rules for dealing with the limits of sequences, right? As if you remember back to Calc 1, you spent a lot of time talking about limits of polynomials over polynomials, and then you also dealt with L'Hopital's rule for the limits of functions as well. So we have two really powerful techniques for dealing with these limits of functions. So just as a quick refresher on what those are, so if we have px over qx, where both these are polynomials, if the degree of px is greater than qx, so we have a polynomial with bigger degree on top, then the limit x goes to infinity of p of x over q of x is either positive or negative infinity, and you can determine which one by plugging in different values and seeing what you get. If the degrees are the same, equals q of x, then we're going to look at the leading coefficient. Remember, the leading coefficient is going to be the term, the coefficient in front of the term with the biggest power. So then it's the limit as x goes to infinity of p of x over q of x is going to be the leading coefficient of p of x over the leading coefficient of q of x. And then finally, if my degrees are smaller, so degree of p of x is going to be less than the degree of q of x, then my limit is going to be 0. Okay, so this is one of the things that you should remember from calculus, and the second is L'Hopital's rule. Oh, I think it's like that. Actually, really fun math story with L'Hopital's rule. So L'Hopital was not actually a mathematician. L'Hopital, I believe he hired Cauchy kind of as his personal mathematician, as rich people were just crazy rich back in that time. I believe it was probably around the 1700s. And his one request for paying Cauchy to just sit around and do mathematics all day was that he had to name some significant result after L'Hopital, kind of like as a thank you for being paid. And so that's why we got L'Hopital's rule. It's actually something that was proved by Cauchy, but under the patronage of L'Hopital, which is really interesting. But anyway, so the idea for this is if the limit as x goes to infinity of f of x over g of x is indeterminate. All right, so some examples of this are 0 over 0, infinity over infinity, things like that, right? Where we can't actually determine what this limit is, then we can take derivatives of the top and bottom. So infinity of f of x over g of x is f prime of x over g prime of x. And then limit as well. And this also works if this infinity here is a number instead of an infinity. But we'll just be dealing with infinity in this case, since that's what happens with sequences. Okay, so let's take some of these results and just see what we can do with them. All right, so if we have my sequence from 1 to infinity, and I say a sub n is 3n cubed over n cubed plus 1. Well, in this case, it is fairly straightforward to see what I might want to have my function be, right? If I set f of x equal to 3x cubed over x cubed plus 1, right, we exactly have that f of n is 3n cubed over n cubed plus 1. So in the case where we have explicit formulas for these a sub n here, we can just copy this explicit formula into the function we are interested in dealing with. The times where this doesn't work is going to be if instead of having an explicit formula, we have maybe a recurrence formula, which will come up a lot when we're dealing with infinite series, because a lot of times we can't explicitly find what these partial sums are going to be, right? There's just no good way of determining this since we're adding some new member of our sequence each time. So in those cases, this method might not work as well, but if we are able to actually figure out an explicit formula for our a sub n's, this method works great. Okay, so we're looking at the limit as x goes to infinity of 3x cubed over x cubed plus 1. Okay, well, this is a polynomial over a polynomial. 3x cubed has a degree of 3. X cubed has a degree of 3. So we are in the second case where both degrees are the same. And so we know that this limit is going to be the leading coefficient of the top polynomial divided by the leading coefficient of the bottom polynomial. So leading coefficient is the term and the coefficient on the term with the biggest degree. So it's going to be a 3 over 1 or 3 as my final answer. So the limit of this sequence exists, and it's going to be equal to 3. All right, another quick example of this, example 2. Let's say now my sequence n equals 1 to infinity, where an is 2n squared plus 1 over n. Okay. So again, I will use the same technique where I just make the n's x's and set the limit as x goes to infinity of 2x squared plus 1 divided by x. Okay. Well, we are again in a case where it's a polynomial over a polynomial. And so what we know in this case is the top polynomial has a bigger degree than the bottom polynomial. And so that means this is either plus or minus infinity. So let's figure out which one it is. Is it positive or is it negative infinity? If we plug in really big numbers here, we have 2 times an x squared. So 2 times x squared will be a positive number, plus 1. So this entire top part is going to be positive as x goes to infinity. Furthermore, this bottom part, this x, as x goes to infinity, will also be positive. So we have a positive number divided by a positive number, which means this is actually just going to be a positive infinity. And so my limit now as n goes to infinity of the members of this sequence is going to be positive infinity or does not exist. Does not exist. Okay, great. So let's do one more example where we're dealing with the transformation of these sequences from integer numbers to actual functions that we're more used to dealing with. And let's do one where we have to use L'Hopital's rule on it. Okay. So example 3 with L'Hopital's rule. is the limit, or we'll take our sequence as a sub n equals 1 to infinity, where we have 1 plus 5 over n to the n. Okay. Same as before, we're going to convert this into x's by replacing all n's with x's, and we have the limit as x goes to infinity of 1 plus 5 over x to the x. And let's just say this is equal to some value L, and we'd like to figure out what L is. Okay, well, if we try to figure this out right now, we have a 5 over infinity, so this is going to go to 0, so we have a 1 raised to an infinity. And this is going to be one of those indeterminate forms where we're not actually sure what this is going to be equal to. So the basic strategy for dealing with these functions, especially when you have exponents in them, is to take natural logs of both sides and then use L'Hopital's rule on the resulting function. So taking natural logs, I can bring natural logs inside my limit. So I have x times the natural log of 1 plus 5 over x equals the natural log of L. Okay. Now, this isn't quite something we can use L'Hopital's rule in, right? Because we don't have a fraction. We have x times the natural log of 1 plus 5 over x. And so what we do instead is say, okay, well, this is equal to the limit as x goes to infinity of natural log of 1 plus 5 over x over 1 over x. Right, it's the same thing, I just divided by the reciprocal of x, which is the same as multiplying by x. And the reason we do this, right, remembering back to Calc 1, is going to be, it's going to give us this nice indeterminate form. So the bottom, as x goes to infinity, is going to go to 0. The top, as x goes to infinity, is also going to go to 0, right? I will get a natural log of 1, which we know to be 0, so this is an indeterminate form. And that means we can now apply L'Hopital's rule. It's very, very, very important to always make sure you have fractions and are in indeterminate form to use L'Hopital's rule. So, limit as x goes to infinity, and now I can take the derivatives of the top and the bottom and compute that instead. So the derivative of natural log of 1 plus 5 over x is going to be 1 plus 5 over x. And then on top of this fraction, we have the derivative of 1 plus 5 over x. The 1 will go away. We're just left with this 5 over x right here. Taking derivatives of that will leave me with a negative 5 over x squared. And on the bottom, similar to the other one, we have a negative 1 over x squared. All right, well, let's do some multiplying. Try to simplify this out, get it just one fraction instead of the 4 or 5 fractions we have right now. So I'll multiply this by negative x squared, which means I multiply this by negative x squared over 1 over 1. Doing this, I have the limit as x goes to infinity. These x squareds are going to cancel with that negative. These x squareds are going to cancel, and so I'm left with a 5 over 1 plus 5 over x. Great, so I'm getting closer. I now just have 2 fractions instead of the many, many I had before. And so if I multiply the top and bottom by x, this is going to be the limit as x goes to infinity of 5x over, the x distributes here, so I have an x and a 5, x plus 5, which is great, right? This is a polynomial. It's 5x over x plus 5. They're both lines. And so what I can do is I can use my polynomial rules for dealing with this limit at this point. They have the same degree. They're both degree 1. My leading coefficients are 5 and 1. And so we know that this limit is going to be 5. Coming back up here, though, we weren't exactly figuring out what L was, right? We were figuring out what natural log of L was. So we know, actually, that natural log of L is 5. And our way to get rid of a natural log is taking e to the both sides. And so I have L as e to the 5th power. Okay. So this means the limit as n goes to infinity of my sequence 1 plus 5 over n to the n equals e to the 5th. Very interesting, right? This is kind of one of those places where e shows up, and it doesn't really make sense why it shows up, right? There's no e's in here at all, but it is showing up because we are doing this technique with the natural logs right here. And that's where we're going to get this e to the 5th. So one very important thing to note about this is that if the limit as x goes to infinity of f of x does not exist, this doesn't tell us anything. So the standard example is if I take my function as cosine of 2 pi x, right? Every time I plug in an integer for this x, I'm going to get 1 out. So it's going to be 2 pi, which gives me 1, 4 pi, which gives me 1, 6 pi, which gives me 1. So the limit as n goes to infinity of cosine of the sequence cosine of 2 pi n, well, it's just a sequence of a bunch of 1s, so the limit has to be 1. But the limit as x goes to infinity of cosine 2 pi x does not exist, right? Because my function, I should start at 1. My function will look like this, so on and so forth. So I'm never ever getting closer and closer to a value. I'm just kind of oscillating back and forth between 1 and -1. And so no matter how far out in x values I go, this limit is not going to exist. So that's just something to keep in mind, is that this technique will not always work. It will always work if the limit does exist. It won't work if the limit does not exist. Okay. All right. So now let's talk about a bit of, or actually let's do one more technique for dealing with these. So one more technique. And this is going to be to use limit rules. Okay, so this is best demonstrated with an example. So the limit as n goes to infinity of n to the 3/2 over n to the 3/2 plus 1. So we can't use polynomial rules on this, right? Because these aren't polynomials. We might think to apply L'Hopital's rule to this problem, because we would get an indeterminate form of infinity over infinity for this if we convert this into a continuous function, which is a great idea. That would actually work for this problem. But let's think about another way of solving this problem. So what I'm actually going to do is I'm going to multiply the top and the bottom by 1 over n to the 3/2. So just do some algebra here. And the reason I want to do this is it's going to leave me with a 1 on the top here, and that will allow me to just deal with the bottom by our limit rules of division. So this is equal to the limit as n goes to infinity of 1, which will just be 1, over the limit as n goes to infinity of 1 plus n to the negative 3 halves. Or let's actually rewrite this as 1 over n to the 3 halves. Well, the limit as n goes to infinity of 1 is just 1, and we can break up the addition here. We do have to be careful that we're not going to get a 0 on the bottom, so just always be double checking your work for this. So this is actually 1 over 1 plus the limit now as n goes to infinity of 1 over n to the 3 halves. Okay. So we have this n to the 3 halves here. What ends up happening with this is we're going to put in larger and larger n values, and we're doing 1 over this. When we do this 3 halves will keep making them larger and larger and larger, so this is actually going to go to 0. And so we have a 1 over 1 or 1. Now, if you'd like to practice your L'Hopital's rule on this, definitely do that. You should get the same answer as 1 for this problem. But this is just another technique that we can use for solving these problems. So to make this a bit simpler, we're going to talk about what's called the geometric series, talk about what the limit of that is, and then we can apply it to more general problems. So we're going to be interested in the series of r to the n from n equals 1 to infinity, where r is some real number. It could be 1, it could be 2, it could be negative 1/3, anything we would like. And we'd like to know the limit as n goes to infinity of this r to the n. Okay. So let's deal with a couple special cases first. So if r equals 1, what's going to happen is we'll have 1, and then 1 squared, which is 1, 1 cubed, which is 1, 1 to the 4th, which is 1 still. And so I just have this sequence of all 1s. And so the limit as n goes to infinity of 1 to the n is just going to be 1. Okay, what about negative 1? R equals negative 1. Oh, let's just rewrite this as negative 1 to the n. Well, this is a bit different now, right? What's going to happen in this case is for n equals 1, I have negative 1. For n equals 2, I have positive 1, negative 1, positive 1, negative 1, positive 1. And so it's going to do this thing where it's just going to bounce back and forth, but it's not actually going to get closer and closer to any value, right? So all of the even terms will stay at 1, all the odd terms will stay at negative 1. So this does not exist. Does not exist. Okay. Well, what about between negative 1 and 1? So for negative 1 less than r, less than 1, so I have some fraction, right? Say 0.5 or something like that. If I do take, as an example, r to the 1/2, I'm going to get as my sequence 1/2, square it 1/4, cube it will give me 1/8, 1/16, so on and so forth. And we can see that as we make this go as n goes to infinity, we're going to get closer and closer to 0. And the same thing is going to happen with a negative. So if I had negative 1/2, I'm going to get negative 1/2, positive 1/4, negative 1/8, positive 1/16. And so it's doing the same thing where it's getting closer and closer to 0, but now it is bouncing around. So it's doing something like this, which we saw some examples of in the previous lecture, but it's still getting closer and closer to 0. And you can also see this from the function for both of these. But the limit as n goes to infinity of Rn, for this case right here, which is the same as absolute value of r is less than 1, is going to be 0. Now, similarly, if r is greater than 1 or r is less than -1, so basically just the absolute value of r is going to be bigger than 1, right? Then we say that this limit as n goes to infinity of r to the n equals for r does not exist. So it's going to either be positive infinity or it does not exist. Does not exist. So it converges rather than diverges, right? So in the case where, say, r equals 2, my sequence is going to be 2, 4, 8, 16, 32, so on and so forth. So I keep getting, wow, that was terrible. I keep getting larger and larger and larger values, and so it's not actually going to converge to any real number. It will go off to infinity, but it does not exist, this limit. So we have our cases where the limit as n goes to infinity of r to the n equals 0 if I am in this case where my absolute value is less than 1. It is 1 if I have exactly r equals 1 and does not exist for absolute value of r greater than 1 or r equals -1. So these are all of the cases we talked about. And so we have this complete classification of what's known as the geometric sequence of when it converges and when it diverges. And now we can use this along with our previous technique of using the limit rules in order to determine what values of limits are going to be in kind of a more easy fashion. So let's look at the limit as n goes to infinity of an, where n is going to be 5 times 0.6 to the n minus 1/3 to the n. And we'd like to know what the limit of this is going to be. So what we can do is we can break this up using our limit rules. So this is the limit as n goes to infinity of 5 times the limit as n goes to infinity of 0.6n minus the limit as n goes to infinity of 1/3 to the n. Include the curly brackets. Okay, so you have a bunch of 5s as your sequence. This is going to be 5. And then the other two are going to be geometric series, right? I'm raising some number to the nth power, so 0.6 or 1/3 to the nth power. And so we can use our previous result in order to say what this is going to be. So in particular, I have a 0.6 raised to the n. Well, r is going to have an absolute value less than 1. And the same thing here, r is going to have an absolute value of less than 1. So both of these, by our calculation of what geometric series are equal to 0. And so my entire function here is 5 times 0 minus 0, or 0. So the limit of a sub n is going to be 0. We're going to get closer and closer and closer to a 0 value. And right, we can see how powerful this is going to be. We don't need to graph anything. We don't need to think about how we can convert this to a function, anything like this. We can just break it up into its different pieces and then use our geometric sequence in order to figure out what each of the individual pieces are going to be. So as another slightly more complicated example, but not too bad, is the limit as b sub n, or we want to calculate the limit as n goes to infinity of b sub n, where b sub n is going to be this 2n squared plus n over 2 to the n, 3n squared minus 4. Okay. So we have a 2 to the n here, or really a 1 over 2 to the n because it's on the bottom of our fraction. And so this is going to be how we're going to deal with our sequence for this, is we're going to split this up based on this 2 to the n here, and then we are going to use geometric sequences in order to calculate. So this is actually going to be the limit, and goes to infinity, of, let's say, 1 over 2 to the n, right? I can always just split up my sequence by multiplication, by my limit rules. So then 2n squared plus n over 3n squared minus 4. Okay, well, geometric series again. This is actually going to be 1/2, right? Which is less than 1, bigger than -1, and so this is going to be 0. So we have 0 times some number, so my entire limit is going to be 0 as a final answer. Right, and we can see from this one right here, this is a polynomial, and so this would actually be 2/3. We have to be a bit careful. We do have to be a bit careful, of if this rightmost multiplication was infinity, right? Because these limit rules we were talking about require the limits to exist. So since this limit exists and is 2/3, and this one is 0, my entire limit of these b sub n's is going to be 0. Great. Okay. So let's now talk about some terminology and then a couple more tests we can do for determining whether these limits exist. So let me pull up a picture about this terminology, which I have right here. Okay. So some terminology is just about sequences. So we say it's increasing if each term is getting bigger. So for example, 1, 2, 3, 4, 5, 6, 7, right? Each term is getting bigger. Some people will also call this strictly increasing as well, to really bring emphasis on that the values can't be the same. So kind of the counterpoint of this is the non-decreasing, where the values can be the same, which we see right here. We have this example of 1, 1, 2, 2, 3, 3. So this is a non-decreasing sequence because the values are the same at points, but it's not increasing because we're not always getting bigger and bigger and bigger. Decreasing and non-decreasing are defined in basically the same way that you would expect. It's just going to be the opposite. So rather than growing bigger, we're going to grow smaller. We're going to go downwards. And then we use this word monotonic, or also monotone will be used as well. I've heard monotone a lot more than monotonic, but if it's either non-increasing or non-decreasing. So it's just saying it's either always going up or staying the same, or always going down and staying the same. So the picture you should have for monotonic is you don't want something like this. This is not monotonic because of this dip right here. So monotonic would instead be something like this, where we might go up for a bit, we might flatten, we might come up a bit more, flatten, and then kind of stay the same. But we're always going up or staying the same, or in the opposite case, we're always going down or staying the same. So the other things are going to be a sequence is bounded above if we don't ever go above some number. So for example, this sequence right here is bounded above because it is, or is not bounded above because we're always going to keep getting bigger and bigger and bigger. And it is bounded below, however, because we're always bigger than 0. So it's bounded below by 0, but not bounded above. Similarly, this sequence right here is bounded above by 2. 2 is the biggest value we have in this, but it is not bounded below by anything because we're going to keep getting more and more negative values right here. And then if both things are true, we say that the sequence is bounded. So for an example of a bounded but non-monotone sequence, we have 1, -1, 1, -1, 1, -1, so on and so forth. So this is bounded, right? It always stays between 1 and -1, but it is not monotonic. Okay. So the reason we care about these is that if a sequence is non-decreasing, so it's always at least going up or staying the same, decreasing, and bounded above, it converges. Right, so the picture you should have in mind for this is we have some sequence and it's bounded above by this line. So it's bounded above. So that means no a sub n is going to get above this, but we're always going up. So we might stay the same and then we might come up a bit more and stay the same. But we can see that we're eventually going to get closer and closer to this line right here. And so if we know that our sequence is non-decreasing and it is bounded above, it does converge. This doesn't necessarily tell us what value it converges to, but it does tell us that this value actually exists, which in a lot of practical applications is really, really helpful because some of the techniques we'll learn in the future will require the sequence to actually have a limit for us to use them. So similarly, bounded below and strictly decreasing also implies convergence, which is just kind of the opposite of this picture I've drawn up here. Implies okay. A good way to think about these, they're going to come up to play a lot in the infinite series, right? Especially this first one here, where it's non-decreasing and bounded above. Basically, if you are always adding a positive number to your sequence, so if every term you're adding is positive, we're going to be non-decreasing, right? We're always adding something to our function. And so a common technique we're going to use is show that, well, our sum can't ever get above some certain value, whatever that value might be. And so because we're always adding something and because we never get above something, we actually show that the sum is going to be convergent. It's going to actually have a value associated with it. Okay, great. And so the third thing, or the, I guess, fourth thing we'll talk about is growth rates, which we'll just go through really quickly. And this is more or less an easy way to tell if a sequence is going to converge or diverge in some very special cases. The basic idea behind this is if I have something like a natural log, right, this is going to grow much slower than n squared. So like natural log grows like this, n squared grows like this. So even in the beginning, if natural log is a bit bigger, eventually n squared is just going to be so much bigger than a natural log of n. So if my sequence looks like something like n squared over natural log of n, I'm going to go to positive or negative infinity and the limit will not exist. Or if I have natural log over n squared, right? I have this thing that's relatively small over this thing that's getting really, really big. And so this is actually going to go to 0. So a formalization of this, which I have a picture of since I didn't want to write it. Okay, so we have these different growth rates of sequences. So basic idea is going from left to right are how fast things grow. So natural logs grow the slowest, then polynomials times natural logs, and then bigger polynomials, and then this is going to be exponential, so you can think of like e to the n or n squared or something like this. We need our b greater than 1. N cube, or sorry, not n cubed, sorry, n factorial, right? N factorial is n times n minus 1 times n minus 2, and then finally n to the n. And the basic idea is that if we have something on the right divided by something on the left, it does not exist. And if we have something on the left, so something small over something big, it's going to go to 0, or it's going to be positive infinity. Right. Okay, so natural log of n to the 10 over 0.00001 n. So limit of this sequence. Natural logs are small. They're on the farthest part over here. Furthermore, this natural log of 10 is the same as 10 times natural log of n. And so we have natural log of n over n. So it's a small thing over a big thing, and so this is going to be equal to 0. Okay. So next one, the limit as n goes to infinity, n to the 8th ln n over n to the 8.001. So just dividing out, we can subtract the 8 from the top and the bottom to get the limit. As n goes to infinity of... Oh, actually, no, we don't even need to do that. So we have rules for this one. So our rules are, if our p is 8, we have n to the 8th natural log, so r is 1, and s is going to be 0.01. So we have a small thing over a big thing, and this is going to be 0. All right, finally, limit as n goes to infinity of n factorial over 10 to the n. Right, n factorial is n times n minus 1 times n minus 2, all the way down to 1. Well, now we have a big thing in n factorial over a smaller thing. So b in this case is 10, which works with this b greater than 1. And so this is going to be big over small, which means our limit is going to go to infinity in this case. So the limit does not exist. Great, so this is how you use these growth rate functions. So this is in particular really helpful if you just have functions over functions in this case. Rather than some more complicated things where we might have multiplication of functions and then division and then more multiplication, or things inside my natural logs. These work really well for kind of these simpler functions with this division. But it is really powerful, and it allows us to figure out these